Acids and bases. According to Bronsted-Lowry's definition, an acid is a chemical species that tends to release or donate one or more protons. When we talk about protons, we're talking about H+ ions. Bases, on the other hand, gain protons given by acids. When you are asked to identify the Bronsted acids and bases, the trick is to find the molecule that is unhappy. Molecules that are unhappy would like to gain or lose a positive charge to help them become more stable. For example, HCl is a very strong acid because Cl- is much more stable in solution than it is when attached to a proton in hydrochloric acid. In this form, it's unhappy, so the dissociation into H+ and Cl- ions is favored. Since H+ ions are formed, we say that this compound is an acid. Another good example is water. Water is happy in its H2O form, but we know that OH- and H3O+ molecules are common and that water can transform into both of them. Water can act as an acid, where it releases a proton to become OH-, or it can act as a base and gain a proton to form H3O+. This kind of compound that can act as both an acid and a base is called an amphoteric species. One way to identify bases is using Arrhenius's definition. A base is a species that liberates OH- ions when in solution. For example, NaOH and KOH in aqueous solutions release Na+ and OH- and K+ and OH- respectively. Therefore, these two compounds are bases. Let's concentrate on one ion at a time, starting with lithium hydroxide. This compound is in an aqueous solution. In water, it will dissociate into Li+ and OH-, and according to Arrhenius, this means that it is a base, not an acid. Looking at HClO3, we see that this compound has an H+ that would be released when in solution. A substance that releases a proton is an acid, according to Bronsted. The same goes for pH4+. The first hint that might tell us that this is an acid is the positive charge. This shows that there is an extra proton in our compound. The ideal situation is therefore for pH4+ to lose this proton and get rid of the positive charge to form pH3. Like we just saw, pH3 is very stable compared to pH4+. It will not want to lose any more protons and therefore is not an acid. pH3 is fairly stable as it is, but a fraction is willing to take on a proton and therefore it's a weak base. Finally, the F- ion has a negative charge. A negatively charged ion will have a tendency to attract protons to stabilize their charge. In this case, F- will gain a proton to become HF, which means it is a base. A conjugate acid is the compound that results from the addition of a proton to a base. A conjugate base is the compound that results from the loss of a proton by an acid. HF is the conjugate acid of the base F-. The right answer is NH3. HCl is a strong acid that will dissociate into H+ and Cl-. Na+ and H+ both have a positive charge, so they're not looking to gain any more protons, which would increase their positive charge. Let's look again at NH3. At first glance, we see it doesn't have a charge, so maybe it's happy and doesn't want to react. It does not need to gain or lose an electron to increase its stability. However, if we look at its Lewis structure, we see that there is a free electron pair on the nitrogen. We know that electrons are negatively charged, so in an aqueous solution, the free electron pair would attract a proton from the water molecule to form NH4+, the conjugate acid of NH3, and OH-, the conjugate base of water. NH3 is fairly stable as it is, but a fraction of NH3 is willing to take on a proton to form NH4+, and therefore it's a weak base.